and the first subcarrier appears to have many cycles. Okay, but I gave you a more accurate view. One subcarrier at baseband would have one cycle during that time period. So if I draw a picture using my journal file, then it would give you a more accurate view. Okay, so in terms of accuracy, please disregard that specific picture. So F1 would have one cycle at the baseband. F2 would have two cycles. Okay, and finally F6 would have 6 full cycles of that sine wave in the same time period of 66 microseconds modulation symbol period. We have multiple cycles. So hopefully that will clarify. And I already proved to you using one specific example that we have orthogonality, and that example is here. So Diane will forward these class notes to you, okay, a little later once we are done with the session. But when you have basically two different subcarriers with specific relationship, meaning the subcarrier frequencies are integer multiples of the base subcarrier frequency, then you can follow this mathematical proof and convince yourself that indeed we have orthogonality. So hopefully that should clarify. But anytime you are not satisfied with my answer, maybe you find it not convincing, or perhaps you want more details, feel free to follow up. Okay, ask another follow-up question. And if my answer to your follow-up question is not good enough, we have a solution. You can stay little beyond the regular session anytime, and then we'll discuss more. Okay? Okay, so that we do not consume too much of the class time. Okay, and okay, pilot, yes, so we need pilot. So the trick question, correct. Okay, so we have some other questions. I'm responding quickly. Okay, another very good question. Why we chose 15 kilohertz? So I'll give you a short answer. The reason that we chose 15 kilohertz is to be able to support high mobility users. In Europe, we have bullet trains. They can move at 300 kilometers per hour, 500 kilometers per hour. So to sustain the radio connection, even at those high speeds, we have this larger spacing between two subcarriers, 15 kilohertz. WiMAX has a slightly narrower spacing, which is 10.94, about 11 kilohertz. So compared to WiMAX, LT will be performing better in high-speed scenarios. Okay, so hopefully that answers. To be clear, and then one final question. The symbol rate is always the same even though subcarriers. Correct. Symbol rate always fixed. So very good comment. So let me again draw the picture. Okay, always remember this rule. And what is the rule? One subcarrier carries exactly one modulation symbol, no more, no less, during our modulation symbol period. Always remember that. And there are different terms. The modulation symbol period, also called useful symbol time, and that would be the same as OFDM symbol time. Okay, same thing, which is 66 microseconds in LT. And if you are picky, 66666, it keeps on going. Okay. Anyway, so if I have F1, this represents one modulation symbol. It does not matter whether I have 4 cycles or 1 cycle. Does not matter. Still, those 4 cycles together constitute a single modulation symbol. So you have made a good observation there, that symbol rate always fixed. Okay. So hopefully that should be pretty clear. But anything unclear or not convincing, okay, feel free to ask questions. The more the questions, the better. And Rhonda, let's unmute the bridge.
Okay, actually, Eric is with us.
Oh, sorry.
Conference has been unmuted.
Okay,
great.
Yeah, I just talked to him this morning. Okay.
Okay, the bridge is now open.
Super. Okay, take this offer. Here is the chance. Hello, any questions? Or you have asked enough through questions and answers box?
I got a question about the symbol, or I guess the carrier spacing.
Okay.
For a given bandwidth, I guess you could get the same throughput regardless of what you set the subcarrier spacing to.
Yes.
There's some optimization.
Correct. You can have more symbols or more subcarriers. Correct. Absolutely correct. You are thinking in the right direction. Correct. I agree. So I agree with your observation. But is there any other follow-up question, or you just wanted to confirm?
I just was curious about that. I guess you mentioned earlier they selected 15 kilohertz for mobility, and I guess there's some trade-offs.
Correct. Okay. And we will discuss that in the next few minutes. What is the trade-off, okay?
All right.
Okay, good. Yeah, but you have made a very good observation. Correct. So you can have either more symbols or more subcarriers. That is correct. Any other comment or questions, concerns, opinions? And we value your opinions. Yeah, someone made a comment that sometimes when I speak too fast, I also write too fast. And then you cannot decode and decrypt what I am writing. So hopefully you have observed some improvement. We would like to enhance based on your feedback. Okay, any other question? But we really appreciate. Okay, you have been asking very good question. Very good question. No one wants to take my offer. Just one question. Just one comment.
I have a question about the center carrier.
Yes.
So I wonder why the question was why we don't transmit at the center carrier. The answer you gave is to ease the center carrier detection.
Correct.
But that will mean that if we rely on the absence of transmission for the detection, then we must use the frequency 1 and the frequency -1. These two frequencies must always be used in priority in order to show up absence of transmission.
Yeah, very good observation.
Right?
Correct. Okay, so okay, good. In the next session that talks about the air interface, I will show you the exact structure of the time and frequency resources. And you will see that we have special signals at that time. Okay. So-called synchronization signals. Okay, and they are always transmitted in specific time period. Okay, and that will help us. But you have very good observation.
Thank you.
Sure, you are most welcome. Any other comment, or you want to confirm something, or you disagree, or anything like that? See, my job is to satisfy your curiosity, okay, in the next few hours. So whatever questions you have, okay, send them my way. Keep those questions flowing my way, okay? Okay, anything else before we go on with the remainder of the presentation? Okay, so Eric, let's mute the bridge, please.
The conference has been muted.
Okay, coming back to our discussion of OFDM. Okay, so OFDM quite efficient because we have parallel transmissions on multiple subcarriers. And what we would discuss next is the challenges that OFDM faces and how we take care of the challenges. Okay. That's the next topic. Now, a student asked a question, why 15 kilohertz? So here you should be able to get your answer. Okay, now let's say we have some user here, another user here, two users. And we have given F1 to one user, F2 to another user. Okay. Just some simple examples. Now, if the users are not moving, no problem, because when the base station looks at F1, this is the signal power that it experiences at F1, and at that time F2 going down, exactly 0. Okay, so 0 interference because we have orthogonal subcarrier. Things will be working just fine. We'll be doing great. But what happens when this user 1 now starts moving toward the base station? The frequency of that subcarrier is now different. It will increase. Why will it increase? Who will tell me? Why does the received signal frequency increase when the user starts moving? Doppler effect. Perfect. Thank you. I got so many answers. Very good. Yeah, all of you are awake. Looks like. Very good. Okay, so this is the Doppler shift. So when the user start moving, then because of the Doppler effect, the actual received frequency will change. So here the user is moving toward the base station, so frequency will increase. Instead of frequency being F1, now it will increase and it becomes F1 prime. So that is the delta F Doppler shift. The faster the user moves, the larger the Doppler shift will be. Okay, so now let's see what is the impact of that. Okay, so let's pretend that we would like to decode F2. Okay, that is user 2's allocated subcarrier. So this is the signal power that we are getting on F2. Now when we look at F2, let's see how much power F1 has. Now F1 has changed to F1 prime. No longer 0. So now we have non-zero interference. Earlier, in this case, when no one was moving, we had perfect orthogonality. No intercarrier interference, no interference between two subcarriers. But now we have started observing that, the signal and interference could come quite close to each other. And when that happens, the receiver has tough time decoding the signal because interference may come dangerously close to the signal. If interference is too much compared to signal, we cannot decode that signal. And then we may have bit error, then the quality will go down, etc. So, basically, because of the movement of the users, we have intercarrier interference. Now, what is the solution? Adequate subcarrier spacing. Okay, so let me draw a simple picture. Okay, so let's say we have narrow spacing between two subcarriers, and F1 and F2. Let's keep it very simple. Here is F1, and the next one is F2. And the spacing between two, let's say 1 kilohertz. Narrow space. Okay. And then we have Doppler shift. So this F2 will move. F2 prime. And if you're trying to decode F1, this is the signal power. And this is the interference power. And the difference between F2 prime and F2, that is the Doppler shift, as we mentioned earlier. Okay, what happens when you have wider spacing? between two subcarriers. Let's say we have one subcarrier here, F1, and this is F2, right? The spacing between two subcarriers is now wider. Okay, now let's say the user is moving, right, at the same speed, so we have same Doppler shift, delta F. So this will be F2 prime. This is the interference power. This is the signal power. Now if you observe here, we have larger difference, right? Meaning our signal is quite large compared to interference. In this case, when we had narrow spacing, the signal is only slightly greater than interference. We have little difference between the two. So when you have wider spacing, even when the users are moving, our signal is still quite strong compared to interference, because the signal and interference, they are apart by a wider margin, maybe 20, 30, 40 dB margin. Okay. So basically, the wider the spacing is, the more Doppler shift we can tolerate. And the UMTS LTE has 15 kilohertz spacing. So that is wide enough to take care of inter-carrier interference even when the users are moving at 300 or 500 kilometers per hour. Okay. So that is why we have chosen 15 kilohertz, that we want to support higher mobility users, and when those users are moving, then they will cause inter-carrier interference. But even in that case, our signal would be sufficiently strong, sufficiently stronger than the interference power, and that will be able to help us get our information bits from the signal. So now you know why we have chosen 15 kilohertz, to make sure that even in the presence of very large Doppler shift, we should be able to decode the signal. Okay. And just for your comparison, here WiMAX chose 10.94 kilohertz spacing. Okay, so it's narrower than the LTE, and that's why LTE should give you better performance in case of very, very high speed. When the users are moving at regular speed, no problem, but if we have bullet trains type speeds, then WiMAX would have a hard time, and LTE will give better performance in those scenarios. Okay. So that's one of the advantages of LTE compared to WiMAX. Okay, we have a lot of answers, so let me just acknowledge and thank you for giving me the answers. And let's see if there. What about? Okay, there are two. Looks like two questions. Okay, what about intersection? At the intersection. Oh, intersection. Yeah, sorry, I do not understand the question. So if you could please provide more information in your question. You say, what about at the intersection? And I do not understand the question. So please submit the question again with some additional information. Okay, and one, can the users compensate for Doppler? Not really, because this is happening in the uplink. So one user is sending signals, right? Another user is sending signals, and those will be affected in the uplink differently depending on the user speed. So the base station is just taking samples of the incoming signal, and in that case we are not sort of individually processing the signal. So the base station looks at the entire 10 or 20 megahertz signal, and then it will pick the subcarriers by using 15 kilohertz spacing. Okay, so in that case, we cannot sort of do the full sort of compensation. Okay, but of course the pilot is a reference signal, and we will use pilot to do coherent demodulation. So that aspect will be working, but in terms of being able to compensate directly using the Doppler shift of pilot, it may be little bit difficult because you have already taken the samples, and when you have taken the samples, then you have equally spaced subcarriers. So you have already picked the sample points in the frequency domain. So it's a little more difficult to fully compensate for Doppler. And again, this is a problem in the uplink. In the downlink, yes, we can adjust because for a given UE, everything will move to the left or to the right of the correct subcarrier position. So then we can do compensation in the downlink. That should be easy, relatively easy, but in the uplink is relatively difficult. But very good question, very good question. Okay, so okay, now another question. So it looks like you guys are taking my offer, huh? That more the questions the better. Good. LT not full. LT is okay. LT supports 3 duplexing methods: the regular FDD, frequency division duplexing, and then we have TDD, time division duplexing, and we have half FDD. So we support all 3, and our current view is that FDD will be the default deployment configuration in early LTE deployments. So early deployments of LTE you will see FDD. Later on you will see TDD, but early deployments FDD. Okay, very good. Okay, so okay, let's see. Solution to the Doppler shift to have wide enough spacing. Correct. So yeah, so someone made a comment that solution to the Doppler shift is have wide enough spacing. Correct. Correct. 15 kilohertz. That is absolutely correct. Okay, then we have another question. Could UE transmit its own speed for Doppler compensation? Oh, so okay, someone has a very good idea. Maybe you should patent this idea. So the student has this very interesting comment that if we have a GPS receiver, then assuming that it gives you good accuracy, okay, I do not know how accurate that would be for the purpose that we are trying to use, okay, because assuming that it gives us good enough accuracy, then yes, the UE can adjust its own transfer frequency, and then it will be received at the correct level, correct frequency at the base. Very good idea. Okay, go ahead, write the patent draft and submit to the US Patents Office. Good idea. But of course, I do not know about the accuracy. Okay, how? But if you have accurate receivers, yes, that will be a very good idea. You are increasing the complexity, but good idea. Maybe then you can eliminate, you can use narrower spacing in that case. Design your own system. Okay. Good idea. That's a good idea. Okay. All the questions have been answered. It's clear. So we are all clear to move forward. So that is one problem, intercarrier interference, because of the movement of the users, and the way to solve that problem is to have larger spacing, have adequate, good enough spacing between 2 adjacent subcarriers. And the good number for LTE is 15 kilohertz. Okay, now another challenge OFDM in general faces is inter-symbol interference. Okay, inter-symbol interference. So basically we are saying we have a direct path here. Part of the energy gets reflected from a building here. Another building reflects some other part of the energy. So even though transmitter sends one signal, our receiver gets 3 copies of the same signal, and that is the multipath. So what will happen? Well, when we are looking at our modulation symbol period, and this would be the direct path coming to us in straight line fashion. But when we are looking at our current symbol, then previous symbol has those delayed copies, so they will be arriving on those reflected paths. So basically, when we look at the current symbol, delayed copies of the previous symbol will start causing interference, and of course that is inter-symbol interference. Different technologies have different ways of dealing with the inter-symbol interference. Okay. So multipaths will cause that, right? And yesterday I asked you guys a question, what is the solution in SC-FDMA, and you mentioned rake receiver. So rake receiver can resolve the multipath, and one finger of receiver can look at one multipath, another rake finger can look at another multipath, and in that case we do not need to fight multipaths, we combine them. Okay. We welcome them. As long as you have enough number of fingers, you are okay. But that is not the case with OFDMA, because in OFDMA there is no rake receiver. In fact, you cannot even resolve multipath. Okay. The multipath automatically add up at the antenna itself. So receiver has no way of separating one multipath from another multipath. So what is the solution? Well, the solution to that problem is a relatively simple, elegant solution: cyclic prefix, cyclic extension. Okay. Prefix or extension. So let's see how to make that one. Here is our regular symbol time, okay, which we call useful symbol time, modulation symbol time, right? Modulation symbol period, whatever you have to call it. 66 microseconds in LTE. So then what we do, we copy part of the waveform and paste it at the front. Copy and paste. Simple operation. So if you paste, it appears as if we were extending the cycle. That's why the name cyclic extension. Okay, now what is the impact of that? Well, when we look at our symbol here, current symbol, the delayed copies of the previous symbol coming on those reflected paths, they will start causing interference. So we have interference here, maybe another interference here, but then no need to worry, because we have put the extra stuff. So once that overlap time is over, we have nice beautiful cycles. 1 cycle, 2 cycles, 3 cycles of sine wave, and so on. So as long as we have enough length for cyclic prefix, then we are okay. So that is the solution to the inter-symbol interference problem. That between the boundary of those symbols, at that symbol boundary, we have to have some extra time, some extra signal, and in a very simple implementation, the user can just ignore the initial portion of the signal and focus on the remainder of the signal, and that should give you nice cycles of sine waves, and then we have good orthogonality, okay, during the useful symbol time. So basically, multipaths will mess up the signals, and the cyclic prefix, cyclic extension will recover the orthogonality because we have the extra time that we can easily discard at the receiver. And the question is how much CP I should have. In UNTS, we have 2 values. We have 4.69 microseconds, that is one value, and we have 16 microseconds, that is another value. So 2 values are supported. So if you are a service operator, then you will pick one of the numbers in a given geographical area, and that will take care of your inter-symbol interference. And we have some questions. Not sure. To understand the okay, Okay, so someone wants to see the impact. Okay. When you have inter-carrier interference, okay, the frequency itself is changing. So instead of having sub F1 as your subcarrier frequency, let's say instead of 15 kilohertz, it will become 14 kilohertz. So the subcarrier itself will have different frequency. In case of inter-symbol interference, even if no user is moving, even if no one is moving, because of the multipaths, we have some signal arriving directly to the UE. Part of the energy will probably get reflected from some other obstruction. So then we have delayed copy. So even if the user is not moving, even in that case, there will not be any Doppler, but even in that case, we will have interference. So the F1 subcarrier frequency we are not changing. It is the same subcarrier frequency. So when you extend the cycle, let's say we are extending cycle here, frequency remains the same. Okay, frequency. We are just extending that frequency for a little longer time. So we are extending the time period. We are not changing the frequency itself. Okay, we are just sending the same frequency signal for a little longer time. So same 15 kilohertz signal, for example, in case of F1, we are sending it for a little longer time. Okay, hopefully that yes. So one simple way to implement to take care of these multipaths is to discard cyclic prefix. A more advanced receiver will do some additional processing. So maybe we do not need to discard the whole cyclic prefix. Maybe 50% of the cyclic prefix is good enough at a given time instance. So a more advanced receiver may do some more processing, but the easiest way is just to discard the CP at the receiver. So that is correct. And we have one more question. Why not just have a guard silence? Oh, very good point. Very good point. So we could have done that. We could have just said, okay, I will not transmit the signal for a certain time period. Okay. Now, the main reason that we do not do that is to have the power amplifier and to have the receiver, because when you have discontinuous transmission like that, then power amplifier doesn't like that. Okay. We want some sort of signals going to the power amplifier. Okay. So power amplifier will work well if you have some sort of continuous transmission. And another reason that we do this extension is it's easy to implement. Okay, because you have already constructed the signal. Okay, let me give you a little more information. Why I say that it's easy to do that. Okay, and for those folks who are just looking for concepts, if you find some details too much, please have patience. Okay. Okay. So one way is, let's say F1, then copy this part, paste it here. Then we have 2 cycles, again copy and paste. So this is one way. Okay. But the typical implementation will not do that. Okay. In typical implementation, what you do is, we will see a little later today that there is some processing, IFFT. So we give all the subcarriers to this IFFT and it will combine the signals. So we already have all these signals that we will transmit. Then we just take the last few samples and add those samples at the front. So very, very easy. So just a single step operation. Just take the last few samples, append those samples at the front, and you are all set. Okay, these two are equivalent. IFFT is a linear operation, so you can do it before IFFT or after IFFT. So very, very easy to implement. Okay, so that's why we do that. Okay. It also helps with synchronization. So that's another side benefit of doing the cyclic extension rather than just having silence interval during that time. Silence interval would work as well, but this will work better. Okay, so hopefully that is addressing your question in sufficient detail. Okay. Now coming back to our challenges. As I mentioned earlier, typical OFDMA system suffers from so-called high peak-to-average power ratio problem. So here is F1 sending one modulation symbol. Then we have F2 sending another modulation symbol. So these are all independent modulation symbols. So for all practical purposes, you can think of them like random numbers. Right? So when you add random numbers, sometimes you will get high number, very large number, and that will result in high peak power. So even though on average you are not using much power, there are some time instances when you really need to transmit a whole lot of power. So this is the problem known as high peak to average power ratio. Now there is the nature of the signal, okay, OFDMA signal. And how do we take care of that? There are several ways of reducing the peak to average power ratio. Okay, and one is of peak clipping, meaning let's say if this is the signal I need to transmit, I will just artificially chop it off here. Okay, this is how CDMA systems work today. So if you need more power than the power amplifier can give you, then you will just chop it off at some level. Okay, so that you can operate in the linear region of the power amplifier. Okay, otherwise there will be distortion. Okay, so that's one way, and you can do that. Another way that WiMAX, for example, supports, it's not mandatory that commercial deployments have to use this, but it could be implemented. It's so-called peak cancellation. So let's say there is one subcarrier F1 given to one user, and then there is another subcarrier, let's say F3, given to another user. So now sometimes they may line up and you may need more power. So in that case, we add a dummy subcarrier. The dummy will just send out a different kind of waveform. So this plus and this minus, it will cancel out, and because of that, it will reduce the power recall. So basically, peak cancellation involves transmission of some dummy subcarriers with dummy signals, such that a part of that signal will cancel out the part of the true subcarriers carrying data. So in terms of overall transmitted signal, we will see that we do not need very high peak to average power ratio. Okay. The peak power and average power, they will come close. But the LTA has chosen to use another approach, which is SC-FDMA. So basically, in the uplink, instead of using the pure OFDMA, we will use the SC-FDMA. Okay, that is the main idea. And how SC-FDMA works, we will see a little later. Okay. So basically, if you want to reduce peak to average power ratio, peak clipping, then peak cancellation, SC-FDMA, these are the example techniques. Time for me to ask you a question. Again, there is a single answer, a single choice. Okay, so and you need to pick the best possible answer. So there are many good choices, okay, here, but pick the one that is the closest match. Closest match. Now, if I were you, I would think this way. Cyclic prefix, what does it solve? Why do we have cyclic prefix? What kind of problem does it solve? Then intercarrier interference. Okay, what is the solution to that problem? Then peak to average power reduction. What are different techniques that help us reduce peak to average power ratio? So think along those lines, and then you will come up with correct answer. Okay. So if you are thinking of A, then do we have cyclic prefix to solve peak to average power ratio? Think. Option B. having adequate subcarrier spacing. Does it help ICI? About C. If we have cyclic prefix, will it help us with inter-symbol interference? Will SC-FDMA help us reduce picture ratio? And so on. Think along those lines. So far I have 50% correct answer, and because we have many good choices. Okay, so many parts are correct, but I'm looking for the best possible answer. Best possible answer. Yeah, so think, do we have cyclic prefix to solve picture ratio reduction? Is that why we have cyclic prefix? Think along those lines. Why do we have cyclic prefix? To solve picture ratio problem, to solve ISI problem. Why do we have cyclic prefix? I will give you 1 more minute. And I will answer that question in the meantime. Cyclic prefix is added by the transmitter. So when transmitter sends out a signal, it will add some extra time. And the receiver, the easiest way for the receiver to process that signal is just discard or ignore the first time period, let's say, that corresponds to cyclic prefix. That would be the easiest way of processing the received signal. So cyclic prefix is added by the transmitter, and we could just discard that at the receiver because it may have corrupted signal due to inter-symbol interference. Okay, looks like you guys have made up your mind. So let me close the poll and share with you the results. Okay, the correct answer is B, C, D, E. B, C, D, E. That is the choice number 4, second last choice. 40% of you chose that. Okay, now let's talk about all these one by one. Okay. Peak to average power ratio reduction in cyclic prefix. Cyclic prefix. We do not have cyclic prefix to solve the peak to average power ratio problem. We have cyclic prefix to solve the inter-symbol interference problem caused by multipath. Right? We do not start designing CP to reduce peak to average power ratio. Okay, so A is not a valid choice. So then it means ABC, right? Wherever you see A, that is ruled out. Okay. Now let's look at B. It is correct that if you have adequate subcarrier spacing, if you have wide enough, let's say 15 kHz in LT, that will help us with the inter-carrier interference. So it is correct solution to the problem. C. Yes, cyclic prefix helps us solve the inter-symbol interference problem. So it is correct. C is a good choice. D. Yes, SC-FDMA is indeed the option that LTE has chosen to reduce picture ratio. And finally, we could use peak clipping to reduce picture ratio. Okay, it is one of the valid options. Okay, so B is correct, B is correct, C is correct, D is correct, and E is correct. So B, C, D, and E. Now some of you chose B, C, and D and did not choose E. So if you are thinking from the LTE perspective, then it is okay. You can choose BCD, because in the uplink, for example, we do not have to do any pick clipping. Okay, so that would be a valid answer also. Okay, so BCD or BCDE depends on your perspective, but the full-fledged correct answer is B, C, D, and E. Okay, the question is general. That is correct. That is yes. So I agree. So I agree with the with your observation that right now this is general theory, right? Because we are right now in the general area of OFDM. We have not started the LTE specific OFDM and SC-FDMA. But you are right. Okay, if you have answered the questions from the LT perspective, I am perfectly fine with that. So I agree with your approach. Okay, very good. Okay, let's move on. So we know the basics of OFDM now. Okay, and before we start discussing OFDMA and SC-FDMA, let me quickly show you how the OFDM transmitter and receiver would work. Okay. So we have here OFDM transmitter, a simplified view. Okay, so we have user data bits, information bits. We protect the bits, for example, add redundancy via turbo coding. So this 0, now we have 3 zeros, 1 becomes 3 1, so we have some redundancy. Do the modulation. Here just one example, 16 QAM. Okay, so one symbol represents 4 bits or 4 code symbols. And now we have modulation symbol. We put one modulation symbol on one subcarrier, another modulation symbol on another subcarrier, and then we give those to the IFFT, inverse fast Fourier transform. This inverse fast Fourier transform will combine the orthogonal subcarriers that are carrying those modulation symbols. It will combine those into a strange looking signal. But inside that strange looking noisy signal, we have orthogonal subcarriers, each subcarrier carrying one modulation symbol during 66 microseconds. So even though it looks like noise, it has indeed inside all those orthogonal subcarriers with modulation symbols. So this is similar to a CDMA signal. If you look at CDMA signal, it looks like noise, right? Over the entire, let's say 1.25 megahertz or 5 megahertz signal. Okay, it just looks like noise. Same way here, this signal looks like noise, but just like CDMA signal has orthogonal Walsh codes and OVSF codes carrying the data, same idea here. Even though we have these noisy signals, looks like a messed up signal. Inside that messed up signal, we have orthogonal subcarriers, each subcarrier carrying a modulation symbol. And this is all baseband. Okay, then we add cyclic prefix, do the frequency up conversion. So now it becomes an RF signal and send that RF signal over the air. And IFFT, okay, how does IFFT work? I am giving you a simple formula here. So basically, IFFT is nothing but a fast way of implementing inverse discrete Fourier transform. And this is the formula. So basically, we have the modulation symbol, and that modulation symbol will be placed on a specific carrier frequency. Okay. So one modulation symbol will go on one carrier frequency, another on F2. So basically, we are converting from frequency domain into time domain. So once you have all maybe 1024 subcarriers, right, then you combine all those signals using this mathematical formula, and you will get time samples. So if you have 1024 subcarriers, you will get 1024 time samples. So for example, this one, these are all samples, 1024 samples. 1, 2, all the way up to 1024. So now you have converted from frequency domain to time domain, and this is what goes over the air, essentially. Still a baseband signal, but then you need to do frequency up conversion. But essentially that baseband signal is going over the air. Okay. So basically n modulation symbols go in, right, on n subcarrier, and then you get those time samples, time domain signals that I just drew here. Receiver will do the opposite processing, so it's getting the strange looking signal. Then we do the FFT, so basically we are taking samples. So we will take, let's say, 1024 samples of this signal. Okay, and then FFT will give you 1024 modulation symbols. Okay, one modulation symbol on one subcarrier, another modulation symbol on another subcarrier, and so on. And then we do the demodulation. It means we'll get those sets of bits back, do the decoding, and you will be able to recover your data. So basically, what separates 3G from 4G is this IFFT. So IFFT at the transmitter is combining orthogonal subcarriers. One subcarrier carries one modulation symbol during the symbol time period, and at the receiver, this FFT will give you all of your orthogonal subcarriers back. Each subcarrier will have one modulation symbol. That is the main difference between 3G and 4G. In 3G, we spread the signal. So one user's signal multiplied by one OVSF code, one Walsh code, another user's signal multiplied by another code, so that we spread the signal. Here, we are giving one set of subcarriers to one user, another set of subcarriers to another user. So one user's signal will be buried inside the total signal. Another user's data will be buried inside the subcarriers that are allocated to that specific user. That is the idea. And again, FFT here is a mathematical formula. So you take the time samples. Okay, so the strange looking waveform that I discussed, you take samples. So those samples go into the DFT, and the time domain, you get your frequency domain. These are your modulation symbols. One modulation symbol on one subcarrier, another one on another, and so on. This is that formula. Okay, so true or false? Right, 50% chance of getting it right. But I hope all of you get it right. Okay. So please do not create a random number from 0 to 1 and use 0.5 as your threshold. Okay, whatever you learn, use that knowledge, please. So think, once we have generated signal, right, inside that combined signal, buried inside that signal, do we have orthogonal subcarriers, each with one modulation symbol or not? Right, when the base station sends out that signal, inside that signal, do we have orthogonal subcarriers? And does each subcarrier carry some sort of modulation symbol? Okay, think from that perspective. Because IFFT is combining all those subcarriers. Okay, so once we combine, do we still have orthogonality? Do we still have symbols on those orthogonal subcarriers? Okay, we have a question. For each IFFT, input repair, yes. So it's amplitude and phase, correct. It's a modulation symbol, so there will be an amplitude and phase, correct. It will be a complex number at the input of IFFT, that is correct. Because if you are using 16 comm or 64 comm, you have amplitude and phase associated with that modulation symbol. So you are right. Amplitude and angle, both correct. Can you give an example for a modulation symbol? Oh, okay, let me give you an example. Oh, maybe we should close the poll. Okay, let me close the poll and share the results. So 73% think that it is true, and that is correct answer. Okay, once we construct the IFFT signal, it looks like noise. Looks like a completely messed up signal. But as I have said, inside that signal we have orthogonal subcarriers, each subcarrier carrying a modulation symbol. Okay, so this is correct. Okay, now someone wants to get an example of the modulation symbol. So let's take care of that. Okay. So let's say QPSK. That is one of the methods, okay? One of the modulation schemes. So let's say 1, 2, 3, 4. We have 4 modulation symbols. Symbol 1, 2, 3, and 4. Maybe this represents with 0, 0, 0, 1, 1, 1, 1, 0, something like that. So let's see S1. This is a modulation symbol. This is so-called I channel, this is Q channel. And what you are seeing here is formally called signal constellation diagram. Okay, so let's see how this symbol will look like. So on the x-axis I channel, let's say this is A. And the y-axis is the so-called Q channel. This is, let's call it B. So S1 is nothing but A plus J times B. It's a complex number. So the amplitude square root of A square plus B square, and the phase or the angle would be given by tan inverse B divided by A. So this is how that signal would look like. And if you want to think from another perspective, I will give you another example. There are different ways of looking at this. Let's say this is the cosine signal and this is the sine signal. Okay, so it would be A times cosine wave at a specific carrier frequency plus B times the sine wave, that is the amplitude of the sine wave. So that is another way of looking at that. So you are combining the sine and cosine signals, each with a certain amplitude, okay, and it will have certain phase. So hopefully that will answer your question. And we have one more question. Output is the sample. Okay. That's why include is misleading. Oh. Okay. It's samples. Okay. So some folks have found the question to be a little bit misleading because we say include. So let's see. Okay. So we said that signal at the output of FFT includes modulation symbols on subcarriers. Okay, so some folks think that maybe I should not use the word include, but what we are trying to convey is that the output signal from IFFT, as you have correctly pointed out, is samples. So when you consider all those samples together during the symbol time period, then all those samples together represent modulation symbols where each modulation symbol goes over one subcarrier. So if you were thinking along the same direction, but you chose answer false because of the word include, that is fine. As long as you know the concept, I am fine with that. Okay. Now we have another question. So you are taking my offer of asking as many questions as possible seriously. We like that. The more the questions, the better. Okay. Inputs to IFFT are complex numbers. Yes, correct. They're complex numbers because they are modulation symbols. Absolutely correct. One modulation symbol, as I just gave an example, is a complex number. Okay, so that is correct. Okay, anything? Okay, we are all clear. No question. We have answered all the questions so far. Okay, now let's see. Okay, we have, okay, I will give you a simple example here of how to design an OFDM system. Okay, so we have a mission. We have a mission to get 20 megabits per second. Okay. We are told that the delay spread is 200 nanoseconds, so 0.2 microseconds. The bandwidth that is available to us 15 megahertz. But there are some subcarriers we cannot use. So 12 we cannot use. Okay, because for some other purpose. And by the way, this is for 802.11. Okay, because we want to just understand the design philosophy. But I will give you some LTE specific parameters later. Okay, so we are told that we need to worry about 0.2 microsecond delay spread. In 802.11 type systems, we use a rule of thumb that, okay, 4 times the delay spread. Again, rule of thumb. Okay, that's good enough guard time. So that will take care of all the multiparts. So we said, okay, the total cyclic prefix time, cyclic extension time is 0.8 microseconds. Very good. Now we need to figure out the symbol time. Now at that time we need to make sure that we don't have too much cyclic prefix. We should have enough time available to send real data. So our useful symbol time, the modulation symbol period, should be long enough. So we said, okay, let's use another rule of thumb, 6 times the guard. We will use that as the total symbol time. So basically we are saying that out of 4.8 microseconds, that will be the total symbol time, total. Out of that, 0.8 is the cyclic prefix and 4 microseconds is our useful symbol time or modulation symbol period, meaning during that time we will have those beautiful sine waves, full cycle. So that is the modulation. Okay, so basically we have taken care of some cyclic prefix and we know the symbol time, the useful symbol time. We know the relationship between the subcarrier spacing and the useful symbol time, inverse of each other. So once you know the useful symbol time, 1 over that will give you the spacing, 250 kilohertz. So that's what we got. We are told that we have 50 megahertz spectrum. So the total number of subcarriers we can squeeze in is 15 megahertz divided by the spacing, 60 kilohertz. But we cannot use all 60 for data. We are told that we have 12 overhead. We are left with 48 data subcarriers. Since we want to get a pretty good data rate, we need to use high order modulation. Let's choose 16-com modulation method. So it means that if we have 48 subcarriers, you can send out 48 modulation symbols, and each modulation symbol is 16-com. So it will represent 4 bits. So using 48 subcarriers, we can send out 48 modulation symbols or 48 times 4 bits, 192 bits. The data rate will be the number of bits divided by the total time period. And including the cyclic prefix, the total time period is 4.8 microseconds. So this is the total symbol time. Total. So that will give us 40 megabits per second. But we just need 20. So it means that we can do coding. So we have 20 megabits per second, and then we will do coding by rate 1/2. So we are doing the repetition in some fashion. That will give us 40 megabits per second, and now we are all set. So basically, we can achieve this 20 megabits per second data rate by using 48 subcarriers, and each subcarrier will carry 16-com modulation symbol. Okay, and we should be able to even do the protection by this rate 1/2. So for every 1 bit going in, 2 bits will be coming out. Okay, so think of that like repetition. Okay, so that's sort of the design idea. Okay, the way we design OFDM systems. And okay, so simple. This was just a simple example to give us some insight into how typical OFDM systems may be designed. Okay. So we have talked about so far OFDM, orthogonal frequency division multiplexing. But what is this OFDMA? Multiple access. Well, when you support multiple users, at the same time you are using OFDMA. For example, in this case, we have a total of 1,000 subcarriers. Each subcarrier carries little bit of data, 10 kbps. So our base station is a big pipe, and that pipe is 10 megabits per second wide. We have allocated in this example 900 subcarriers to one user. So during that time interval, this user gets 9 megabits per second. At the same time, another set of subcarriers, let's say some 99 subcarriers, are allocated to another user, and that user experiences 990 kbps. Same idea, another user, we just give one subcarrier. Again, this is generic. Okay, this is generic. Okay, and it means that that user has very little data rate, 10 kbps. Say this guy is reading voice or IP, no need to give high data rate. So as you can see, at a given time instant, I'm supporting in this case 3 different users. So whenever we support multiple users at the same time, we are using OFDMA. If you focus on let's say link between the base station and this terminal, then what we are doing? We are using multiple subcarriers, 900 subcarriers, right? Maybe F1, F2, all the way to F900. So whenever we have parallel transmission on multiple subcarriers, we are using OFDM. So we have OFDM here between one user and base station. We have OFDM here between base station and the user. Okay. So, but from the cell or base station perspective, many users can access the system at the same time because we can allocate them different subcarriers. That's the OFDMA. OFDM for multiple users at the same time, that will give us OFDMA, multiple access. Okay, now we will talk about LTE. Okay, so we have a very good foundation, and now we are ready to discuss how those concepts are used in the LTE standard. Okay, so let's see. Okay, okay, maybe this is a good time for a break. Okay, so let's have a 10-minute break, and once we come back from the break, we will have opportunity for you to ask questions using the audio bridge, and also once we come back, we should be able to specify the LTE design parameters, right? How LTE uses the concept that we just described. Okay? So you got 10 minutes